So in this problem, I have the guy on the unicycle just sitting there, and I'm going to treat this one wire as if it's two separate wires because they're two different angles. Now I also want to do a little bit of geometry here. Think about this being a horizontal line. Let's see if I can draw it. Something like this going across. And that's going to make my two triangles. I know that that's going to be 90 degrees. This corner here is 55. So when I'm looking at this, I want to find this angle here, and that's going to be 35 degrees. On the other side, I have 65 and I have a 90-degree angle, and I know that they all add up to 180, which makes this angle right here 25 degrees. So when I draw my free body diagram, I'm going to use the 25 and the 35. That's why I'm doing this. And a little bit as I work through this, I'm going to have to erase this drawing to make some room, but we'll just leave it up there for the moment. All right, let's start with the free body diagram. The first free body diagram I'm going to do, I'll put a dot right here. And then I'll just give myself some kind of coordinates. Start with a dotted line here and another dotted line here. So I have some idea of what I'm doing here with X and Y. And then the first angle I'm going to have is going to be the tension on the right wire. So I'm going to call that TR, and that's going to go to the right. Let's see, 35 degrees. Something like this. Right, and that's going to be 35 degrees, and that's going to be tension on the right. On the left side, that's 25 degrees. So over here, I'll pull 25 degrees, something like this, and that's going to be 25 degrees, and that'll be the tension on the left. And then going down, I'm going to have the weight. Looks something like this. So that's the weight of the rider, which is the 655 newtons. Awesome. No normal forces because I don't have any surfaces. All I have is the two ropes kind of pulling off, and I have the weight going down. I know some of you are thinking, well, there's a normal force between the rope and the wheel, and that's true, but this isn't that kind of problem. We're not looking, you're over analyzing the problem if you're looking at that. So here I've got my free body diagram. Now, when I look at my free body diagram, nothing is perpendicular to anything else. So what I need to do is redraw this with components that are parallel and perpendicular to each other. So that's what I'm going to do next. So I'm going to redraw these two, redraw everything that I have here. So I'm going to use my technology to do it for me. So there it's redrawn. And then what I'm going to do is I'm going to break up my TR and my T left into horizontal and vertical components. So at the 35 degrees, I'm going to start here at the free body, go over, and then to add vectors, I've got to go tip to tail. So there's the tip and there's the tail. That makes this TR the adjacent side, so that's going to be cosine 35 degrees. And this one's going to be TR sine 35 degrees. Now once I do this, I'm not going to use these two in any expressions anymore. Once I break up the trig, that's supposed to be a sine. There it is. Oops, let me see if I can clean that up just a little bit. Right, just a little bit neater. Sine 35. On the other side, I'll do the same thing. I'll start with the free body diagram and go over. And I'm drawing it around my angle, and then I'll go up. So let me tip to tail like that. And then the adjacent side to 25, that'll be TL cosine 35. And then this other side, I got to write it over here as TL sine 25. And you probably see the same mistake I do. 35 here should be 25. 25 degrees. All right, so I'm going to use the second free body diagram for all my analysis. So I'm going to pause here for a moment while I clean up the diagram. There, in the blink of an eye, I've cleaned up everything. So this is the free body I'm going to use, and made some space on the screen. So I'm going to start by summing up the forces in the x direction. So I will sum up the forces in the x direction. It's not changing speed in the x direction. In fact, it's just sitting there, so that's going to equal to 0. So that's equal to the tension, let's see, the force going to the right minus the force going to the left. So I'll do TR cosine 35 degrees minus TL cosine 25 degrees. Now sum up the forces in the y direction. So I'll sum up the forces in the y direction. and that's equal to 0. So I'll make all the forces up minus all the forces down in this case, since it's equal to 0. So I've got 2 forces going up and 1 going down. I've got, let's see, TL sine 25 degrees going up plus TR sine 35 degrees going up minus the weight. So I'll just call that W. All right, there are a couple ways to solve it. From here, it's just math, so there's lots of ways to get the final answer. I'm going to show you one way to do it. Since a lot of these problems I do a lot of substitution, I'm going to stick with the idea of using the method of substitution here. So what I'm going to do is I'm going to isolate TR from the top equation by summing up the forces in the x direction. So if I do that, I get that TR is equal to, well, let's back up a second. I'll slow down just a little bit here. TR cosine 35 is equal to TL cosine 25 degrees. Now that means that TR is equal to TL cosine 25 degrees divided by cosine 35 degrees. So now what I'm going to do is I'm going to take this expression for TR and put it in wherever TR is located when I'm summing up the forces in the y direction. So let's see, I think I can put that down here in the bottom. So that means that, let's see, 0 equals TL sine 25 degrees plus, and this is going to be that fraction for TR, which is going to be TL cosine 25 degrees divided by cosine 35 degrees times sine 35 degrees minus the weight. So hopefully you can see what I did there. I just replaced TR here with TR there. I made that substitution. Now there's something else that's kind of cool about this, and that's the sine 35 divided by cosine 35. So that's here, sine 35, cosine 35. According to our trig identity, sine over cosine is tangent. So really when I'm looking at this equation, it's actually 0 is equal to TL sine 25 plus TL cosine 25 times, I said plus there, I said TL plus, I think it's TL times cosine 25 times tangent 35 degrees minus W. The only reason why I want to do that, it just takes up less room on the page. It's kind of simple to work with. All right, so there's my trig identity. It's all set up there. Now, next step. I'm going to isolate the W all by itself. So W, if I move it to the other side, is equal to TL sine 25 degrees plus, is that right? Yeah. Plus, whoops, TL cosine 25 degrees tangent 35 degrees. Now what I'm going to do is I'm going to use the distributive property and pull TL out. So W is equal to TL times the quantity sine 25 degrees plus cosine 25 degrees times tangent 35 degrees. And then I'll isolate TL by dividing both sides by everything that's in the parentheses. So TL is equal to the weight divided by sine 25 degrees plus cosine 25 degrees times the tangent of 35 degrees. Now we know what the weight is. The weight is 655 newtons. So when I'm doing the math, I'll just take that and put in 655 newtons. And do the math, and I get the tension in the left is equal to it's like 620 with 3 sig figs newtons. It's actually 619 point something, but so we'll go with that. Now, to find tension in the right, I got to use one of my previous equations. I am going to use the fact that, I'll put it in a different color just to make it stand out a little bit. TR is equal to TL cosine 25 degrees divided by cosine 35 degrees. So TR is equal to my number that I got, which is 619.5483, and some other decimals are in there as well, times cosine 25 degrees divided by cosine 35 degrees. So TR is equal to 685 newtons.